Let's start sharing the screen. Now you should be seeing the presentation, I hope. What I will do as well is share the talk on the chat. The main reason I want to do that is in case you want to look at the references, then I've included hyperlinks to all of the references. So this way you can just look it up. So I've just sent the PDF of the presentation to the chat. Okay. So today I'll be telling you about some moderately recent papers that we've been writing with Eric Method, who's a postdoc at École Polytechnique. And what we've been interested in is the fate of so-called normal charge densities at very low temperatures in superfluids. And I'll try to explain to you why we became interested in this question and what we found about them. So the references on which the talk is based are these two papers that we wrote over the last year or so. So you can find them online. And the plan of the talk is as follows. I should perhaps also say, please feel free to interrupt me at any point. I've seen that there are a couple of holographers in the audience, so you'll probably you won't learn much holography from me today, but still feel free to ask questions, and other people feel free to ask questions anytime. So I'll start with a brief review of effective theories for superfluid hydrodynamics. Then I'll tell you a little bit about holographic superfluids, that is how we model superfluid systems using gauge gravity duality. Then I'll tell you how we can compute the normal density using gauge gravity duality. And finally, I'll briefly mention some links on to experiments on high Tc superconductors, which were a big motivation for us to start investigating these systems. Okay, so okay, so what is superfluidity? Superfluidity is the spontaneous breaking, follows from the spontaneous breaking of a U1 symmetry. So that means one of the big consequences is that the mass or the charge, depending on what U1 we're talking about, would be transported without friction by the condensate. This is a big macroscopic effect. In particular, for superconductors, it means that you transport electrical current without generating any heat. And so that obviously is something very interesting to happen. From a theoretical standpoint, so these systems have been much studied. One of the simple systems that exhibits superfluidity is the simple field theory of a complex scalar with a Mexican high potential. So here, capital phi is my complex scalar. It has a mass, it has a coupling lambda. And if both these couplings are positive, then there's a non-trivial ground state, provided some quantity mu, which is the chemical potential, is greater than the mass. And then the non-trivial ground state is this one. So you can expand around this ground state. And then you will discover that there's a phase degree of freedom phi, which is a gapless mode. It has no mass. You can excite it without energy cost. And this is actually the Goldstone boson that follows from the spontaneous breaking of the U1 symmetry. Now, sometimes we don't always have at hand a microscopic description, but what we do have is a universal description of such systems at long wavelengths and low energies. This is called the Landau-Tisa hydrodynamic model for the two people that came up with it originally. What this model assumes is that gradients are small, so this is the same assumption as we would usually have in hydrodynamics compared to the local equilibration scales. So time gradients are small compared to the inverse of the local equilibration time at which local equilibrium is established. spatial gradients are, roughly speaking, small compared to the inverse of the mean free path. Now, in order to describe the dynamics, what we do is we start from the symmetries of the system. For the systems at hand, this will be translation symmetry, rotation symmetries, and I will assume relativistic symmetry for simplicity. So what we'll have is conservation of a relativistic stress energy tensor, and we'll also have conservation.
No, we don't need to go both of us.
Now, I'm assuming relativistic symmetry for simplicity, but the same, I think everything I'm going to tell you should hold also without relativistic symmetry. Just to set up some notation, at equilibrium, there's a fluid velocity u mu, which has -1 as a norm, and the metric is Minkowski, eta mu nu, with mostly plus signature. So time has a minus, but spatial indices have a plus. Then we want to solve this system. So right now, this is just fluid hydrodynamics. And I will start with this, and I'll add the superfluid. So we give constitutive relations to both of these conserved quantity, to T mu nu, the stress energy tensor, and to the current J mu. And at ideal order, which is what I'll be concerned with in this talk, and also only be concerned with linear hydrodynamics, then at ideal order, the stress energy tensor can be expressed in this simple form. This is just energy density plus pressure times u mu u nu, and then we add the pressure term proportional to the metric. This is essentially telling you that TTT, the time component of the stress energy tensor, is the energy density, and that the spatial components are the pressure. The current is going to be the charge density times the velocity. So current will flow when charge is transported by the system. We also have the Small law that relates the sum of the energy density and the pressure to the temperature times entropy density plus charge density times chemical potential, and then the first law of thermodynamics. Now, with all of these ingredients, the system of equations is closed and you can solve them. And in particular, obtain retarded Green's functions, obtain the profile of flows, etc., etc. Now, we want to spontaneously break the U1 symmetry. When we do that, as I've explained on the first slide, we expect that there's a new gapless degree of freedom. And generally, that this gapless degree of freedom will commute, will have a non-trivial commutator with the charge density, which is the density that's generated by the symmetry that we've spontaneously broken. Now, that equation has an important consequence. If you look at the time dynamics of that Goldstone mode, then you look at the commutator of the Goldstone mode with the Hamiltonian, which is the Hamiltonian that's where we've added a chemical potential. So then we see that then you see that there's a piece H that commutes with phi, but then this piece does not commute with phi because of this non-trivial commutator. And this is essentially going to tell you that the time derivative of phi is minus the chemical potential, which we can rewrite as u mu d mu phi equals minus mu after we boost that equation. There are also modifications to the constitutive relations and to the thermodynamics compared to fluid hydrodynamics, which are all these terms in red. So you see that now the Goldstone mode contributes to the stress energy tensor. It contributes to the U1 current in such a way that now you see that you have two types of flows. There's what I would call normal flow, which is transported by the fluid velocity. And then there will be superfluid flow that's transported by the condensate. This normal flow will be dissipative generally, and this superfluid flow will be non-dissipative. And then we have some extra modifications to the first law of thermodynamics, which won't really play a role here because I'm assuming that there's no background superfluid velocity. So this term, in the absence of any background superfluid velocity, it does not contribute. There are also important consequences on the spectrum of hydrodynamic modes. There are new gapless modes, as I've said. And in particular, the Goldstone mode mixes with the usual charge diffusion mode to give us a superfluid sound mode. So this is a mode which is linearly dispersing with a Voigt vector to leading order, and that has a superfluid sound velocity, c squared, which is given by this particular expression. So this is completely fixed by the thermodynamics of the system. You see that there's a ratio of the entropy density over charge density. This is proportional to the superfluid density, as you might expect. It vanishes when the superfluid density is 0, and then there's some thermodynamic derivative in the denominator. So the picture you have in mind is that in a fluid, the modes of the system are the usual first cell modes that transport longitudinal momentum and pressure and energy. Sorry. And then there would be two diffusive modes, a mixed charge entropy diffusion mode and a transverse momentum mode. Now, when we turn on the superfluid, this mode, this diffusive mode for charge and entropy, mixes with the Goldstone mode and give us this superfluid sound mode. So there's a big qualitative difference in the spectrum of modes once we have a superfluid. Now, a remark that will be somewhat important for what follows is that these normal and superfluid densities that I've introduced, these are parameters of the infrared effective theory. You see they enter here in the current, and this is the expression of the current in this long wavelength late time limit where hydrodynamics is applicable. In particular, they are not related in any simple way to the charge residing in the condensate, which is a parameter of the UV microscopic theory. So for instance, if you think about helium-4, you can measure how many atoms are actually condensing, and you realize that the condensate contains less than 10% of the total number of atoms. And this fraction, this condensed fraction, has nothing to do with the actual superfluid fraction with rho s, as I'm going to tell you just now. So what people typically do is that they assume that at 0 temperature, the system of, say, helium-4 can be described as a gas of free phonons. So the phonons here is the usual terminology in this field for the Goldstone mode. You assume Galilean or Lorentz boosts. And then what you would find is that at 0 temperature, the system becomes completely superfluid. That is, the superfluid fraction is equal to the to 1. It's the superfluid density is equal to the total charge density, and that the normal density, and you find that the normal density vanishes. So you see now that even though not all atoms are condensing, still all of them behaves, all of them contributes to superfluidity, let's say. So to reiterate the point, at 0 temperature, the system is in this case completely superfluid, and the phonons govern the low energy dynamics. You can turn on a small temperature, and then what you would find, which, for instance, you can find in this computation, in this review for superfluid hydrodynamics, you would find that the normal density is equal to the entropy times temperature divided by c squared. Now, this is a really nice expression, and you may suspect that this is a universal expression, and you would be right. This is something you can derive in full generality with this particular assumption, that your system is a gas of free phonons and that you have either Galilean or Lorentz boosts. So now now that we've obtained the normal density and we've determined the thermodynamics of the system, we can go back and plug this in this expression for the second sound, for the superfluid sound mode. The first sound mode we find is equal to c. Here, c, I should have mentioned, is the effective speed of sound in the infrared theory. The superfluid sound mode simplifies to c squared over d, where d is the number of spatial dimensions. And this is a prediction that was made by Landau a long time ago. And it follows directly from this assumption that in the infrared at low temperatures, your system behaves as a gas of almost free superfluid phonons. You can recover all of these results more rigorously in the relativistic case, thanks to some formalism that was set up by Damson. He wrote up this universal quantum effective action for relativistic superfluids, which assumes that the Lagrangian of the system is a functional p of some quantity x, which is the square of the gradient of the phase. This is essentially fixed by symmetry. And then if you start computing, then you realize that P turns out to be the thermodynamic pressure of the system. Sun was working at 0 temperature, but you can generalize this to small non-zero temperature, and this way you add the normal fluid density, the normal density. More recently, people have computed the temperature dependence of the normal density in this framework, and they found an expression which slightly generalizes the expression I showed you before. There's now an extra factor of CIR squared, where again, CIR is the effective speed of light in the infrared. Since you assume that there's an emergent Lorentz symmetry, then that emergent Lorentz fixed point may have a speed of light which is not exactly equal to that of the UV speed of light. There are a few questions that we might like to ask. First, do all superfluids necessarily fall into this universality class? So can they all be described as an almost gray gas of phonons? Moreover, you can study the Bardeen-Cooper-Schrieffer theory of superconductors. Then you would find a slightly different result for the normal density. You would find that it's exponentially suppressed at low temperatures. This is essentially because in BCS superconductor, you have an actual gap that develops at low T. So that gap exponentially suppresses the normal density instead of having some algebraic suppression. However, you might wonder what happens in strongly coupled superconductors, such as high Tc superconductors or superfluids that we study using gauge gravity duality. And in fact, as I'll show you now, there's evidence that the picture that we just described is not always correct. So before I go there, are there any questions? Okay, if not, then I'll continue. So let me briefly tell you a little bit about high Tc superconductors. These are materials that were discovered in the mid-80s. People instantly developed a lot of interest in them because they became superconducting at rather high TCs. Right now, the state of the art is that they can become superconductor at temperatures order 150 to 100 kelvins under certain conditions. And it became clear very, very quickly that we could not describe these materials using BCS theory of superconductivity. They have a rather complicated phase diagram. This is temperature versus doping. These are all copper oxide-based materials, and the doping here relates to changes in the chemical composition by substituting atoms versus others. And it allows you to vary the number of available charge carriers and drives the system under a number of phase transitions. At low doping, these are insulators, but at larger doping, there's this superconducting dome that develops right here. And for most of the talk, I'll be interested, at least what I'll tell you during the talk relates to recent results that were obtained by Bozovic in 2016, where they measured the superfluid density in very overdoped LSCO. So this is one of the high TC compounds films. So what they saw two surprising features. These are plots of the superfluid density versus temperature and doping. And so they found that in the very overdoped region, the superfluid density is actually anomalously low compared to what you would expect using BCS theory of superconductivity. And they have this anomalous linear in T behavior, whilst BCS theory in the presence of disorder would rather predict a quadratic temperature dependence at low T. And in the paper, Bozovic and co-authors have very strong arguments why these systems fall outside the BCS paradigm, even though there was some consensus. There's a kind of consensus that this region of the phase diagram should be thought of as a Fermi liquid, and that the superconductor here should be BCS-like. So this is why the results made a big splash back then. Further information came in this paper by Mahmoud, which also has Bozovic and Armitage as co-authors, where they measured the AC conductivity of the same superconducting films in the overdoped region. So you see that they have results for various dopings where Tc is really is rather low, 27 kelvins, then 13, then 7. And what they saw is that there's a very modest loss of spectral weight below Tc. So the orange curves right here are all above Tc, and the blue curves are at very low T below Tc. And as you can see, instead of having a big exponentially suppressed gap developing, as you might expect for a BCS superconductor, you have very modest variation of spectral weight, the more overdoped you go. They summarize this in this plot, where they plot the ratio of the total spectral weight divided by the spectral weight in the normal density, in the normal phase. And here they have various quantities. So S delta is the superfluid density. SU is the normal density in the superfluid phase. And the blue dots are the sum of the two. So you see that the yellow dots are the sum of the two. So you see the yellow dots are roughly equal to 1 within experimental uncertainties. And here 1 is telling you that the sum of the spectral weights that they measure is equal to the number of free electrons or conducting electrons in the normal phase. So this is a consistency check. But with this consistency check, what we see is that the more overdoped you are, so the more you go to this side of that plot, the horizontal axis here is Tc. So when Tc becomes larger, you're going towards optimal doping. When Tc becomes smaller, you're going towards the edge of the superconducting dome. So for the very overdoped samples, you see that most of the degrees of freedom remain uncondensed or normal, let's say, and very going into the superfluid, in the superfluid fraction. So this gave them further evidence that there was a non-vanishing normal density at 0 temperature, which is at odds with BCS and at odds with this result that I quoted before. This vanishes at low temperature. So something is going on here. Are there any questions on this before I move on to gauge gravity duality? Okay, now I'll continue. I've prepared a very brief primer on gauge gravity duality because I think some people here in the audience might not be familiar with gauge gravity duality. So bear with me if you are, and if you're not, please feel free to ask questions. If you would like to know a little bit more, I will try to answer them, but I might not spend too much time discussing general features of gauge gravity duality in the interest of time. So gauge gravity duality is something which was discovered by Maldacena in 1997, and roughly speaking, it states that gravity in a certain type of spacetimes called Untitled Chapter, which are solutions of general relativity coupled to a negative cosmological constant. So gravity in these spacetimes is dual to certain strongly coupled quantum field theories, more specifically matrix large N field theories. If you understand what those words mean, very good. If not, that's okay. In one spatial dimension less. So the gravity theory are defined in d+2 dimensions, where these number of spatial dimensions. And the quantum field theory is on the so-called boundary of ADS, and is defined in d+1. The outshot is that you can map the complicated dynamics of these strongly coupled quantum matter, quantum field theories, to Einstein's equation in Untitled Chapter coupled to a number of matter fields. So this regime, which you would otherwise have a lot of trouble to describe, you can now map to a gravity problem, which you can actually solve. One hint for this duality is that this spacetime Untitled Chapter has the same asymptotic symmetric group as a conformal field theory. So this conformal field theory will be our UV fixed point. If you think of an RG flow, then here we have a CFT in the UV. Now, once you accept this duality, you need some dictionary in order to relate quantities that you compute in the space-time, so in the bulk, as we call it, to quantities in the field theory, which are typically endpoint functions of operators. This is what we are interested in. So typically we're interested in one-point functions of the stress energy tensor, of the current of some scalar operator, and the retarded Green's function, etc., etc. So according to the dictionary, a thermal non-zero density state in the dual QFT is described by a charged black hole in N-theta. This means that we'll be considering renormalization group flows from a UV CFT, which is roughly speaking defined here at the boundary of space-time, deformed by some relevant operator, and they flow in the IR to some non-trivial IR fixed point, which is captured by this black hole. Now, the conservation of the boundary stress energy tensor and boundary global U1 current follows from the bulk gauge symmetries, which are diffeomorphisms and gauge transformations. As I told you, the bulk theory is some Einstein gravity theory, so this has diffeomorphism invariance, and this diffeomorphism invariance directly gives you conservation of the stress energy tensor. It may also have some charged matter, let's say some Maxwell field that has some Maxwell field strength. And then the gauge symmetry in the bulk will give us conservation of a global U1 in the boundary. If I have some scalar operator in the scalar field in the bulk theory, then I'll have some scalar operator in the boundary theory. And the way we read off this data in the field theory is that we solve for these fields in space-time, and then we use this radial coordinate that allows us to interpolate between the black hole horizon and the boundary. We expound all of these fields close to the boundary, and then we can read off all the one-point functions from the asymptotics of the bulk fields close to the boundary here. So this is the rough way how the holographic dictionary functions. Now, how do we have a superfluid? How do we realize superfluidity in the boundary theory? We do it exactly the same way we would do in the QFT. We spontaneously break the bulk U1 symmetry. So here's the kind of gravity theories we consider. As I said, we have gravity, so we have the Ricci scalar curvature, which is made up of second derivatives of the metric. We have a Maxwell field in the bulk, so electromagnetism. Then we have some scalar field eta, which is complex, and which is charged under the U1 symmetry. So there's a covariant derivative here. And what we ask is that this eta gives rise to a non-zero expectation value at the boundary, but without being sourced. So there's a way to do that, which was discovered by these people right here. What they found is that at low temperatures, there exists a solution in the bulk where the field, the scalar field condenses close to the horizon. So it has some non-trivial radial profile, and there's some sort of lump of charged scalar matter in the bulk. And this is your condensate. So to give you a little bit more intuition, as I said, take helium-4, then some of the atoms go in the condensate and some do not. And here, the equivalent picture in the bulk is that you have two types of charges. There's some charge on the horizon, which emits some electric flux. So the horizon here is charged under this U1. And then there's some scalar matter in the bulk, which is also charged. And you can think of this condensate, this charge that sits in the condensate, as the same as the number of atoms in helium-4 that are condensing. And the total charge density, which you read off in the boundary theory, is the sum of these two components. You are also able to compute, so this is a plot of the condensate versus temperature. This is just to show you that there's some minimum temperature Tc, above which there's no condensate, and below which the condensate develops, and then it goes to some finite value at zero temperature. So this is how we describe superfluidity using holography. Now, importantly, all the solutions that were constructed originally were shown to obey the Landau-Tisa model of superfluid hydrodynamics. So if you like, this is further evidence that this holographic system does realize a superfluid in the boundary theory. So what it means is that people computed holographically all the expectation value for the stress energy tensor, for the current, etc. And they showed that it took this form, including the dependence on the superfluid phase, which is essentially the phase dual to the phase of this charged complex scalar in the bulk. So this gives us a lot of control over that system. Now what we wish to do is we wish to compute the normal and the superfluid densities in these holographic superfluids. And for this, we need to extract the one-point functions. More particularly, we need these two. We need the TTX component of the stress energy tensor, which takes this form in terms of the thermodynamic quantities, and ux, the velocity along x, and the gradient of the superfluid phase. And then we also want the x component of the current, which has this form. Now, under the dictionary, these operators, they're dual to perturbations of the bulk, gauge field, and metric. So what we are interested in is the linearized perturbation of the x component of the bulk gauge field and the linear perturbation of the tx component of the metric. And these variables obey second order differential equations, which are just Einstein and Maxwell's equations in the bulk. And there's a whole machinery, holographic machinery, how to solve this type of equations that is now very well controlled. Since we're only interested in thermodynamic quantities, then we can only consider dependence on this bulk radial coordinate r, so that coordinate that allows us to interpolate between the black hole horizon and the asymptotic boundary where we read off the one-point functions. And so we can set frequency and wave number to 0 in the equations. So Herzog and Yaram solved these equations in 2009, and they obtained this type of results. So this is showing the ratio of the superfluid density over the total density versus temperature over the critical temperature for various values of the parameters that enter in the bulk action. So here Q is the charge of the complex scalar, and U characterizes the scalar potential. Now you see that for certain values of the parameters, this ratio goes to unity at 0 temperatures, here as well. So this is all exactly according to the expectations of this effective, this universal effective action that Damson wrote down, and everything seems to, to be okay. But back then, they also found these cases where none of these curves appear to go to unity. So they didn't go to that low temperatures, but we repeated the calculation. If you go to lower temperatures, you definitely do not see these curves sharply bending up and going to unity. So something's going on here. And you could ask, why is this not going to unity? This seems to suggest that in this spacetimes, there's some residual normal density at 0 temperatures. But there was no interpretation of that feature back then in this paper. So we revisited the issue, and in brief, what needed to be done is to be careful about the low temperature expansion of these various quantities and the dependence on the spectrum of deformations around the 0 temperature ground state of the system. And what we discovered is that there are two deformations that are particularly important for our purposes. There's one deformation which breaks the particle hole symmetry, and another one which breaks the U1 symmetry. So schematically, this is the equation that we were solving. This is an equation for the X perturbation of the gauge field in the bulk. And these GTT, GRR, etc. are all the metric functions in the background, same as AT here. So you see that there's a kinetic term, which depends on derivatives with respect to the radial coordinate. And then there are mass-like terms right here, and there are two of them. So this one here just turns on density. This one is non-zero as soon as the density of the dual field theory is non-zero. The dual field theory state is non-zero. And this one is non-zero when you have a condensate. And what turned out to be very important is the competition between these two terms at low temperatures. And the competition between these two deformations actually controls the behavior of the normal density at low temperatures. So in order to go further, what we needed to do is to understand the zero temperature ground states of the model. Again, this is something that was worked out back then, but somehow the dots were not connected. They didn't look more closely at the normal density back in those days. These people, they considered a Paulick potential for the scalar field. And under that assumption, they showed that there were two types of infrared geometries. So what I mean by that is that, again, we have this picture of the entire space-time. Near the boundary, there's this, this is where the dual field theory is defined, and the space-time is asymptotically anti de Sitter. And now we're asking what happens close to the horizon at very low temperatures. And there are two things that can happen. We see that the metric either goes back to another copy of anti de Sitter. So that means that there's here some emergent infrared fixed points with Lorentz symmetry and conformal symmetry. The metric looks like this. You can see that this is scale invariant, as you would expect of a CFT, because if you scale T, R, and X by some scaling parameter, let's say lambda, then this metric is left invariant. So that's one type of ground state that were found in these papers. But there's another type of ground state that is also allowed by the equations of motion, which has which displays an anisotropy between the scaling of time and the scaling of space, which is captured by this Lifshitz exponent z, which is strictly greater than 1. And whether you reach one fixed point or the other one, this depends on the behavior of the gauge fields in this region of spacetime. If the gauge field decays sufficiently fast, then you land on the ADS2 fixed point. So you have an emergent conformal symmetry fixed point in the IR. This you can intuitively understand in the following way. You have your gauge field, it has a time component, it's like a chemical potential. So this wants to break the isotropy between time and space. But if it decays as an irrelevant deformation towards the IR, then the effects of this anisotropy are washed out in the infrared, and you have something which is Lorentz invariant. On the other hand, if the time component of the gauge field, if the chemical potential is important at low temperatures, then this back reacts on the spacetime as a strong anisotropy between time and space, and you land on this Lifshitz fixed point. Right? This is the intuition behind the appearance of these two types of infrared fixed points. Another result that we found is that if the Lifshitz exponent is comprised between 1 and d plus 2, then we're in a phase where this term dominates in this equation that we use in order to determine the normal density. And then we could compute analytically that the normal density takes the same form as in this universal effective field theory that Damson wrote back in 2002. And where CIR here is some effective IR velocity, which is temperature dependent if the Lifshitz exponent z is different from 1. So this is really the same as the EFD result, but now we see that it is also extended for values of z which are less than d plus 2, where, let me remind you that d is the number of spatial dimensions. So these cases, if you wish, are sort of conventional in the sense that they behave exactly according to these EFT expectations, etc., etc. If we look at the temperature dependence of rho n, then we can see that it goes like this with temperature. So d plus 2 minus z over z. And it vanishes as t goes to 0 if this condition is met, but naively it diverges. Something happens if z is sufficiently large, and then this power is negative. And actually what we found is that if z is greater than d plus 2, there we're in a regime where what dominates at low temperatures are the effects of this particle hole breaking deformation. And then if you redo the calculation with this assumption, you'll find that the normal density actually goes to a non-vanishing constant at 0 temperature. Now, as a side remark, in all of these holographic superfluid phases, rho in, which is the charge behind the horizon, so this contribution to the total charge density always vanishes. So at 0 temperature in these systems, the condensate contains the entire density, and there's no density behind the horizon. There are no uncondensed degrees of freedom left, and yet the system does not become entirely superfluid. So this relates back to my comment that I was making on this slide, which are that the normal and superfluid densities, these are IR parameters, but they're not related in any simple way to the charge residing in the condensate. Okay. Then we also verified all of this numerically. We could compute the normal density of the low temperature behavior of the normal density in 2 dimensions for various values of the exponent z. We've got a case with z equal 1, a case with z equal 2, and a case with z equal 12. Now, the formula I've showed you in the previous slide predict the number of temperature dependencies, t cubed, t to the 2/3. And as you can see, the numerical results show that these scalings are very well obeyed. So this is the summary so far. We've found that the normal density vanishes in holographic phases, which are dominated by a specific type of irrelevant deformation that breaks the particle hole symmetry. Whether you want them. The normal density vanishes in holographic phase where it is not the particle hole symmetry breaking deformation that dominates, but it's the U1 symmetry breaking one that does. And our calculation reproduces exactly the expected EFT results for phases that have z equal 1, that have an emergent Lorentz symmetry. And it extends it, it shows that you can generalize it very simply to Lifshitz invariant phases that have z greater than 1, but less than d plus 2. However, the cases with z greater than d plus 2 are qualitatively different. The normal density is non-vanishing. And this appears to be unrelated to the presence of charge behind the horizon, that is, to the presence of uncondensed degrees of freedom. And this explains these observations that were made earlier in holographic literature. Any questions before I move on to the last part and conclude? Okay, so this leaves us with a few open questions. That is, in these Lifshitz invariant phases with z less than d plus 2, we found this particular result. So again, there's some temperature dependence here and rho and vanishes. But if you plug this result in the expression of the superfluid second sound velocity, then you would find that it also vanishes as t to the 2 minus 2 over z, which you might have expected based on dimensional analysis, right? This is exactly what dimensional analysis would tell you. But the starting point of these quantum effective actions for superfluid hydrodynamics is that at 0 temperature, you have a Gaussian mode that governs the dynamics. So how can it be that the second sound velocity vanishes? Because then that would suggest that there's nothing that propagates at 0 temperature. So this raises the question of how we generalize this formalism of the quantum effective action to phases with Lifshitz symmetry. Z less than d plus 2, it should be still qualitatively similar to the free Fronon gas picture with some modifications. But for z greater than d plus 2, we saw that the normal density is now non-vanishing. So we expect that the ground state is very different from the free Fronon gas picture, and most likely extra degrees of freedom are needed in order to explain these results. Now let me come back to the question of Tc superconductors and how these results can shed some light, some qualitative light on these experimental observations. So to capture this sort of behavior, we consider the more general action, where on top of the charge scalar, we've added some other neutral scalar operator in the bulk. And the main reason that we've added this is that it allows us to consider more general zero temperature ground states. Now, instead of having Lifshitz or ADS ground states at zero temperature, we can have ground states that are conformal to these spacetimes. So now they are no longer scale invariant, they're scale covariant because of this extra factor. In a perhaps more intuitive way to describe them is that they violate hyperscaling. By that, I mean that if you compute the way that the entropy density scales with temperature, then you see that it doesn't scale in the way that you would expect in a Lifshitz phase. So T to the D over Z, there's this extra dependence on that exponent theta. So there's some effective spatial dimension, which is now D minus theta rather than D. Now in these holographic systems, we have the following types of RG flows. So again, in the UV, we start from some flow, that's some UV fixed point, which is a CFT. So it has Z equal 1, and there's no hyperscaling violation. And at low temperatures, the system can choose to go to two types of different phases. One is a phase that has an emergent Z equal 1, so emergent Lorentz symmetry, but violates hyperscaling. And the zero horizon electric flux, so the system becomes fully condensed at zero temperature. On the other hand, here, the system flows to a fixed point with non-trivial Lifshitz exponent and non-trivial hyperscaling violating exponent. And some degrees of freedom are left uncondensed. So the horizon remains charged. And the condensate always acts as an irrelevant deformation of the normal ground state. So now, if we go through the same computation for this type of system, we compute the normal and superfluid densities, and we compare this to the normal state density, then we can obtain a phase diagram which is qualitatively similar to that obtained by Bozovic and company and Mahmoud and company. That is, we vary some UV parameter, and we find that in the very overdoped quotes regime, then most of the degrees of freedom go into the normal density, and very few of them go to the superfluid density. And as you vary that parameter in this direction, then gradually there's a transition to a system where no normal density remains at zero temperature, and the system becomes entirely superfluid at zero temperature. So the specific holographic model itself, I don't think is very interesting. I think what is more interesting is the general lesson that this is a consequence of the quantum critical properties of the underlying normal ground state. And this is not an effect due to disorder, which would induce pair breaking, etc., etc. This is really just a property of the underlying normal phase. And it would suggest that in real systems, whether the normal density vanishes or not depends on the spectrum of deformations around the ground states and the nature of interactions in the effective field theory that governs the low energy dynamics. And that, of course, as far as Coop rates are concerned, is still a very open question. There are no firm theoretical results on what the ground state might be. But I guess my message is that if we understand this better, then it might explain a number of observations, such as that of Bozovic. Or that, let's say, Bozovic results are a manifestation of the properties of that unknown ground state. Okay. With that, I'm done, and thank you very much for your attention. I'll be happy to listen to your questions or comments. Thank you.
Thank you, Blaise, for the interesting and so very pedagogical or like overview like talk. I'm supposing there are questions, so please unmute yourself and just ask. So So okay, let me maybe start. So I was wondering. So you were introducing these expressions of like both the T and also the current J, and there was this additional term which is had this rho s divided by mu structure, where mu was the chemical potential.
Mm-hmm.
So how should I envision here the limit mu going to 0? Is there?
So if mu goes to 0, then nothing can condense. You need a non-zero mu in order to this phase only exists at finite chemical potential.
Okay.
This you can see perhaps more simply from this simple classical theory model.
Okay,
this
so you're
only exists if mu is sufficiently large.
Okay, so okay, fine.
This is really a finite density effect.
Okay. Are there other questions here? Like, I mean, okay, let me maybe ask one more, since I don't really know these holographic methods, but so you showed these plots as a function of T over Tc, for instance.
Mm-hmm.
Can these models make predictions about Tc, or should I think of it more like a Landau theory, where Tc is just like a parameter that I set, and
Yeah, I think it's more like a parameter, like you said.
okay.
That Tc can vary a lot depending on the specific type of theory that you pick here. In particular, I don't think these models are well suited to explain why Tc is high. Let's say. This is not a good question for holography.
Okay.
But you see, I've tried to give you an example of what might be a good question for holography, which is, let's consider a superfluid, a system in a superfluid state. Does the normal density always have to vanish?
Yeah.
And if it doesn't, how does it scale given the scaling properties of the ground state? This is something that you can answer using H gravity duality.
Okay, thank you. Are there any further questions? Well, that doesn't seem to be the case. So I will stop the recording. I will post the recording, yeah, probably later tonight, tomorrow. Yeah, and then we can reconvene in 2 weeks, and Glenn Wagner will be the speaker, and he will talk about, say, the more like typical condensed matter approaches to hydrodynamic electrons. But let me first thank Blaise again.
Thanks a lot, everyone.
I enjoyed the talk, and yeah, let's reconvene in 2 weeks.